Welcome, everybody. I'd love to introduce Qianxiao Li from the National University of Singapore, and he'll be teaching us about scientific machine learning, how to learn thermodynamics from using machine learning methods. Welcome, Qianxiao.
All right, so thank you very much for the invitation to speak here. My name is Qianxiao Li from the Department of Mathematics and Institute for Functional Intelligent Materials in Singapore. So my interest is broadly on the intersection of deep learning, machine learning and deep learning, and also dynamical processes. So I'm interested in various theoretical aspects of deep learning and its relationship with dynamical processes. If you're interested in that, I'm happy to talk more on that as well. But today I'm going to talk about something in the reverse direction, which is how do you use machine learning to understand certain dynamical processes. Okay, so the problem I interested in here is certainly not a new problem in science. Okay, so to a certain extent, how to construct dynamics from data is an extremely old problem. It dates back to perhaps the first foray of humankind into quantitative sciences, is where people try to build, particularly Ptolemy and others, a dynamical model for how planets move in the sky, right? So this very famous epicycle models, examples of that. But of course, we have come a long way since the time of Ptolemy, and Newton's laws could be seen as some sort of universal law for macroscopic systems, and then Schrödinger's equation substitutes all of that with some much more universal description of physical processes. So certainly constructing dynamical models from observation is not a new problem. In fact, it's a solved problem, right? Hey, if you think about from Schrödinger's equation viewpoint, where you can describe any kind of system using this many-body Schrödinger equations. So what's left to do? But the problem is really stated in this very overly quoted thing from Paul Dirac in 1929 that pretty much all the underlying physical laws of physics and chemistry are known, right? So the only difficulty has been pushed to the applied computational mathematics, which is how do you solve this equation? But it turns out that these equations are usually very, very high dimensional and they're very difficult to solve. Okay, so until today, almost 100 years later, we're no closer to be able to solve these equations. So was one way of mathematician's way of attacking a problem is if this problem is too hard and solve some other problem. And we have certainly come a long way in physics by not solving these equations directly using computers, but to do something else. So, for example, one way to model these high-dimensional microscopic dynamical systems is to turn to macroscopic aspects. Okay, so if you think about one very familiar example, which is the modeling of gas particles, right? So if you think about all the molecules in the room, right? Currently, whichever room you're in, there are many molecules there, and they're all moving. Right. So if you want to really describe the state of this air particles, air molecules in your room, you need a very high dimensional dynamical process. Okay, one for each molecule atom. Okay, you want to consider. However, you don't really care about the individual positions and momentum of every single air particle, right? Perhaps you only care about some macroscopic quantities, like what is the pressure that is exerting on the room's walls, or what is the temperature, what is the volume in the entire room. So in order to understand, for example, how this this pressure evolves, then it's not necessary to know all the position and momentum of every single individual molecule, but what you need is some other macroscopic quantities. We call it closure coordinates. In this case, we know from ideal gas law, right? The PV equals NKT. So VAN and T are some other macroscopic observables. And together, we can form some thermodynamic description of the system in terms of some equation of state, right? So, but here, when I really say thermodynamics, I mean it in a much more general sense, in that it is some equation that relates macroscopic quantities together. Okay, and this equation, although it's certainly a very reduced description of the air molecules motion, it is enough for a lot of problems involving prediction, analysis, and control. So, for example, to increase the pressure in the room, you just need to increase temperature, and vice versa, right? So that's enough for a lot of control problems. Okay, so the goal here is really trying to do this, but not for a very well-known idealized problem, but for other systems. And turns out that for other systems, especially for systems of some dynamical nature, how do you find closure coordinates, right, to describe the coordinates you're interested in? And also, how do you construct this thermodynamic, or more generally, a macroscopic dynamic description? Is very difficult. Okay, it requires a lot of knowledge about the system, and the question is, can we automate this process using machine learning? Given that now we can produce data and we have access to a lot of computation. Okay, so that's the problem I want to talk about today, and in this particular example about polymer chain that we'll talk about later, that is used to illustrate this process. So. As a applied mathematician, I like to give at least one slide on what is the exact mathematical formulation here we're talking about, right? So here we're given some microscopic degrees of freedom. We call it x, big X, okay, that evolves with time. So it depends on time, and this is a very high dimensional vector. Right? It's big D is very high dimensional, and we're not interested in the evolution of this very high dimensional vector, but on some low dimensional state of interest. For example, Z, we call it Z star, which is the deterministic transformation of the high dimensional coordinates. Okay, so Z star lives in the much lower dimensional space, D1. For example, later we'll see that this could be just 1. Okay, and our goal is to model the evolution of this macroscopic state of interest. So to do that, we need to do 2 things. Okay, the first thing is to find some other macroscopic state of coordinates or variables, z hat, which are also deterministic transformations of the microstate. So why do we need to do that? Is because Z star is usually very low dimensional, so there's no reason to assume that you will evolve as a closed system. So these are basically sufficient descriptors that enables us to model the evolution of Z star. And then together, we want to form a closed equation. Okay, and how do you find the closed equation? You probably need, or we'll talk about that later as well, to find a closed equation so that we can use that to do all sorts of predictions and analysis. Okay, so to give you one example, and this is a precise example we're going to apply our methods to. You can think of the polymer problem, which is a very classical problem in polymer rheology. Is that if you take the polymer, long polymer, you think of a DNA chain, and you put it in some fluid and you suspend it there. What happens is that either due to self interactions or just due to pure entropic forces, this long polymer chain will kind of coil up together. Okay, and when you apply some force in the horizontal direction to stretch it, okay, so clearly it will stretch. Now, one question that people are very interested in is what is the what is the rate of this stretching? How does it depend on how much force you apply to it? Okay, so if you go from a very naive viewpoint, you can think of, okay, so I can apply some force to stretch the coil, and the coil has some restoring forces because it doesn't want to be stretched. So if my force is too weak, then nothing will happen. Right, my stretching force is too weak. But if I stretch it, strongly enough so that the polymer starts to stretch out, then you can imagine that the restoring forces, which is usually electrostatic or otherwise nature, will become weaker, and then you will continue stretching. So what you expect is that if I increase the stretch rate, strain rate, then there is a sharp transition. Below which nothing will happen, and above which then the polymer will completely stretch. Okay, so this is what we imagine could be the case. But it turns out that this is very interesting, because when the people did experiments, bulk experiments, to measure what is the average length of this polymer as a function of how much you stretch it, people find that it is quite a gradual thing. Okay, so instead of increasing very sharply, the average length is increases gradually. So this was a very troubling thing for scientists at the time. But later on, this two landmark papers was basically explaining why. So why this is the case is because the picture I talked about before, where you have a sudden transition, is exactly right on the single molecule level. So each DNA molecule or each polymer does behave in exactly that way, but different polymers, due to some randomness, they stretch at entirely different times. Okay, so the right hand side, this plot shows each of this trajectory is a polymer, and the y-axis is how much it stretches, and x-axis, you can think of it as how much is being stretched, how much is being stretched, and y-axis is how much it actually stretches. Okay, so you can see that each one of them, there is a sharp transition, right? So some of it stretches very quickly, some of it wastes a long time and then stretches, and some of it never stretches at all. So if you average all of them, you get a very gradual curve. Okay, so what this is saying is there's really very strong heterogeneity in the dynamics. But what is not known from these papers is that why different molecules stretch differently. And that's the question we're going to answer today using machine learning. But nevertheless, in this situation, xt, you can think of it as a very high dimensional vector, which describes the coordinates of each individual constituent molecule in the polymer. Okay, so this is a very large dynamic dimensional system. But we don't care about the entire evolution of all these coordinates in the polymer. What we care about is a very low dimensional quantity called z star. Okay, and this is just the length or extension of the polymer at time t. So basically, it's the length along the horizontal direction of the polymer. Okay, so this is a very small one, and this is a large one. So that's what we care about. Okay, so our goal is to model z star and explain the strong heterogeneity in how it stretches, extends. Okay, so let's look at some viewpoints of how you build this dynamical model from data. So essentially, from learning dynamics from data is certainly a very large body of work. But one can think of them as roughly categorized in two directions. The first, I call it database approach, is that you start with some data set, and then you try to build a model. And what you can do is to start with a model of very high complexity. Okay, so you can think of the hypothesis space as pretty much all possible models you can think of. How can you do that? Well, you can just use your favorite large neural network model, like transformer or a large ResNet or whatever. They are universal approximators, so you can approximate anything you want. But of course, this is not the end of the story, because we are trying to build some dynamical models for a physical process. It has some constraints. For example, it has to be energy stable. It shouldn't blow up in finite time and whatnot. So you can impose the desired structures through some regularization function, which means that you penalize everything, let's say, that falls outside of this triangle. Let's say that these are not physical, or we don't want them. Okay, and we only want something inside. But you add that as some sort of regularization. So in the end, what happens is your learned model will try your best to fit the data, okay, but also tries the best to conform to these regularization terms. So what you get is something in between, right? It fits the data pretty well, especially in places where it conforms to the regularization, and also it sort of interplays in between otherwise. So this model is usually very accurate, but the problem is that they do not really respect this structure that you impose, right? It just respects in some sense on average. The other approach, however, we can consider this model-based approach. So this is something that maybe is much more familiar to mathematical modeling of physical processes in general. This is basically what we do all along. So what we start, the way we model this new process is that we can start with some known model. Okay, this model is something that in a very idealized situation, but we know them. Okay, and this is certainly not good enough to describe the data set at hand. So what we do is that we can generalize this model to a much larger set of models, okay, but still with all the right structure that we want. Okay, so all the models we consider has satisfy exactly the structures that we want. Okay, and then within these models, I'll try to find the best one that fits the data set. Okay, so what you will get in the end is some model that is a generalization of some idealized model, and that it tries to fit data as best as it can, while always respecting the constraints of symmetry that you place on the system. So this one, you will get something that maybe is not quantitatively as accurate as the left-hand side, but what the advantage is that you can actually, be sure that whatever model you trained is always going to have the structures that you want, and you can also then, investigate these structures after you train them. So it's perhaps, although it's not as quantitatively, accurate or flexible as the left-hand side, but it gives a lot more information. And what we're going to talk about today is on the second side, okay? And let's look at how we can build such a model. And the known model that we start with, so this little triangle here, is the following original principle due to Lars Onsager, which is the most general and perhaps the only known description of non-equilibrium dynamical processes that are near equilibrium. So you can think of it as something that is at rest, equilibrium, everything is stable, and then you give it a small perturbation and watch how this perturbation dissipates back to the equilibrium. And we can describe that dynamics by the following equation. So this equation is called the Onsager principle, where z is some generalized coordinate, and v is a generalized potential. So it's some potential energy function, or you can think of it as a negative for entropy, depending on the system, or more general free energy. Okay, so v is some energetic function, and m here models the rate of dissipation of energy as it relaxes towards equilibrium. Okay, and m here is shown to be symmetric under some basic assumptions and positive definite. So this is the so-called reciprocal relation. So what we're going to use is to use this as a model for how this z that we will discover evolves.
So let me understand this.
Yeah.
Just from the looks of this thing, it looks like you have, first of all, you assuming near equilibrium. So the pushes are small enough that you always keep coming back to the same equilibrium. So in an energy wheel, you keep pushing up and back, up and back, that kind of thing, like a harmonic oscillator kind of a thingy.
Yes. So you can basically derive this equation exactly from, let's say you are currently at some Boltzmann distribution according to this free energy, this energy function V, and you give it a small perturbation that's Gaussian in nature, and then you ask what is the restoring dynamics from that. Now, of course, we're not assuming V is strongly convex in the sense that it must only have one minimum. You can have many local minima, and this description will be local to each minima.
And you can this allow you to switch across minima in this formulation.
So in this formulation, you cannot, because this is a deterministic process, right?
Okay.
So each basin of attraction will be attracting, but later we're going to generalize to one that could.
Okay, got it. Thank you.
Yeah, which is exactly on the next slide. Okay. By the way, how much time do I have for this?
About an hour. I mean, hour total.
Okay, sure.
About 40 minutes left.
Okay. Yeah. Yes. Please let me know any other questions. Okay. So here, to basically, that's a good question to go to the next slide. Is that now we can we know that problem, that description is very limited in the sense. First of all, it's kind of in a linearized regime, and the second problem is that it cannot really model any noisy processes. So what we're going to do is to generalize this Onsager principle, and we call it a generalized stochastic Onsager principle, GSOP, which adds some terms. Okay, so the energy function is still here, the dissipation function is still here, but now we assume that this dissipation matrix M is still symmetric positive definite, but it depends on the coordinate. So it's a function of the coordinate. Okay, it's a matrix value function. And this is to model the fact that the rate of dissipation could depend on the state. And then we also add a anti-symmetric term, which is models the conservative forces that is present in the system. Okay, something that doesn't change the energy levels, but still could be there. And finally, we add a Brownian noise term with some thermal fluctuation scale sigma, which also could depend on ZT in principle. And so BT is a Brownian motion. So this you can think of as a direct generalization, the big triangle of the Onsager problem. Okay, so the Onsager principle. And again, MWV, sigma, they all have some structures that we impose to it. Okay, so this is going to be the model we're going to fit to the data. And you might ask the question, okay, why do we generalize it in the following form? So let me say a few things about the good thing about this generalization. The first is that this general form includes many known physical dynamical systems. Like, for example, the Langevin equation for coarse-grained molecular dynamics, describing the motion of some particles in a well U, subject to some Brownian forces as well. And this one can be written in the previous form. And also a large class of stochastic Poisson systems, things that you can use Poisson brackets to model, and they can also be written in the previous form. So it includes a lot of very well-known physical dynamical systems. So it's quite general. And the second reason is the following. This is kind of an important one called invariance, in that if we assume that our x coordinate follows our generalized stochastic Onsager principle, which we know many systems do, like molecular dynamics. Okay, it follows our principle with some m, w, v, and sigma. Okay, in this form. Then, if we change coordinates to z by some approximately invertible transformation phi, okay, then we know that the evolution of z, the new coordinate, also follows some form of Onsager principle with some error terms, of course, so it's approximately equal, but with some newly defined m tilde, w tilde, v tilde, and sigma tilde. Okay, so these are not the same energy functions, but they also have the same form. So in other words, the form is invariant, approximately invariant under coordinate transformation, which is something really important to us because we want to model the macroscopic z, the macroscopic dynamics. And we really want the following, where if the microscopic dynamics satisfies, which we know a lot of systems do, satisfies this GSOP, then our macroscopic coordinate should also satisfy GSOP with some other functions that we want to learn or discover.
Okay, so question here.
Mm-hmm. Yeah.
You're pointing to symmetries as, coordinate transformation is a really standard valuable symmetry. Isn't that something you can enforce using your data set? Standard symmetries in image recognition is rotate the image, change the color balance, and so on. So make sure the model is invariant across those symmetries. Can't you enforce the symmetry in the training set?
So here, the symmetry I'm talking about is rather precise. Is in that this m, for example, is a symmetric function. So that means if you take any z, it will produce an m which is a symmetric positive definite. What is positive semi-definite? That's the sort of symmetry I'm talking about. And of course, w is anti-symmetric, right? So this one, later on, we're going to model M and W and V with some neural networks, and we can build the neural networks in a way that it always produces symmetric functions, symmetric matrices as a result. So we're going to enforce this from our model.
And the benefit, presumably, is that this is provably, what's called coordinate invariant, not approximated coordinate invariant.
Oh, okay. What I mean invariance is okay. So I'm not exactly sure if I understand what you mean. Here, the invariance I'm talking about is the invariance of this hypothesis space in some sense. That means if I have one coordinate, okay, that obeys this principle, then if I transform the coordinate, then this principle is approximately also obeyed, but with some other functions. Now, this m tilde and m they are exactly symmetric.
I see. What I'm trying to tease out is to what extent the structured approach gives you benefits over modifying the training set to have examples with the coordinate transformations baked into the training set. So what's a good way of ensuring these invariants?
Okay, so the training data I have is basically some trajectories of x, right? So this is all the data that I have. So in here, I don't think it's straightforward to let's say do some data augmentation or transform so that you capture all the right. So you train, even if you train any arbitrary model, you will have this form. So this is going to be a form that's imposed on the model itself that cannot be just imposed on just preparing the data set in a way. So for example, you can't do data augmentation so that whatever model you train have the symmetry. I don't think it's possible in this case.
That makes sense. Thank you.
Yeah. So in other words, we're looking at a much smaller set of models that have some very specific structures. Yeah. Thank you for the question. Okay, so besides this invariance property, the last property that is also good for us is that it produces some stable dynamics. So by stable, what I mean is that no matter how you train this, the M, W, V, and sigma, okay? So as long as it satisfies the previously imposed conditions, like symmetry, anti-symmetry, positive definiteness, you can show that the energy V, okay, evaluated on your trajectory, in your macroscopic coordinate Z, on average, it's going to decrease monotonically to about the order of thermal fluctuations. Okay, so this is a mathematical, description. But what it says is basically the rate of dissipation is indeed controlled by your M. So your M is really like a dissipation matrix. And if you build your model in a way that V is lower, V is bounded, has bounded level sets, that means it's like you can think of it as grows sufficiently quickly, then we know that the system has to be stable. Okay, so it's something that stability can be ensured a priori. Okay, no matter what training data you feed to it. Okay, so for example, this is another example where you cannot really enforce this without directly enforcing some structure in the model, because even if you prepare even all your data set is entirely stable trajectories, if you train them, it's not necessarily true that the dynamics that you train in the end will always produce stable trajectories. This is not the case. But here, no matter what dynamics you train, you always produce stable trajectories. Okay, so let me just summarize the workflow, and then I'll talk about the actual results that we have for this problem. So this is the overall workflow, which we call it stochastic Onsager net, named after Onsager. So we are starting with some macroscopic coordinates. So this is the data that we have, okay? And we want to model some macroscopic coordinate of interest. Okay, so in the polymer example, this X will be some trajectories of this microscopic polymer evolution as you stretch them using some elongational field like this. And then our macroscopic coordinate is basically just one-dimensional. It is the chain extension length. Okay, so this is one-dimensional. We only care about this extension length. So the first step is that we have to discover some closure coordinates that maps X to Z. Okay, and this closure coordinates, we're going to use a neural network to model the relationship between X and Z hat. And this is going to be learned from data. And this neural network is a very simple network. We call it PCA ResNet. So it's a residual network of the usual sense. But instead of having the identity connection as a skip connection, we'll use the PCA transformation, the principal component transformation, as the skip connection. Okay, so the skip is again not trainable, but online. But of course we can compute the PCA offline. Okay, so the reason we do that is because we want to make sure that later on we're going to look at what the coordinate we actually discovered, right? And we want to make sure that a priori it is as disentangled as possible. So we really want uncorrelated components, right? So that we can interpret them separately. So this PCA connection ensures that it has a strong bias to learn some uncorrelated components. Okay, so then we can concatenate these two together to form our reduced coordinate space. We call it Z, and we want to fit the equation on Z. So the way we fit the equation is to use our stochastic Onsager net, the stochastic Onsager principle, where the matrices M and W and the potential V and the thermal fluctuation sigma, they are just modeled all by neural networks. Okay, and we'll model neural networks in a way that these symmetries are always preserved. For example, the way we make sure this M matrix is positive semi-definite is that we just parameterize the usual matrix value function using a fully connected neural network, and at the end we take the transpose of that network and then multiply it by itself, right? So then you always get a positive semi-definite matrix as a result. Okay, and in this symmetric matrix can just be the original matrix value function minus its transpose. So this always gives you an anti-symmetric matrix. Okay, so we can do that from the model building stage. Okay, so this will give us then a closed equation that we can then use for prediction and also some analysis. Okay, so are there any questions about this overall workflow? So this is basically what we do.
Yes, so it seems like you hopefully have two ideas. One is dimensionality reduction, which I mean could be just there by itself. You could have done an encoder thing, do your neural net on the encoded, encoded state, and then train anything. But so you did that, but you also concatenated that with the macroscopic variables because presumably they were there and already low dimensionality. Was that the idea?
Yeah, so this Z star is already something that we want to model. This is known by the problem, right? So this case is how long the polymer is. And you can think of the dimensionality reduction part as more like a closure thing. So that means that we're not just blindly reducing dimensions. We want to reduce it so that we can describe the Z star. Okay, so this Z hat is going to be also a low dimensional coordinate. And we're not claiming that Z star and Z hat together could fully describe X. But what we're saying is that Z hat is enough to describe Z star.
So how did you ensure that? Because it looks like they're two separate outputs of two different processes. How do you connect them?
So basically, after concatenating them, we're going to train a model that predicts the evolution of this combined coordinate, which depends on Z star, right? Which will include Z star. So if we can train a Markovian kind of process here that can describe Z star, then we have found the right coordinate, right? So in other words, if we could reduce the error here, then we have found the right closure coordinate. So basically, what we're going to do is to train them together.
So you will have gradient backpropagation to the entire thing. So you will adjust the hat if the second stage step does not work.
Yes. So if you have a bad coordinate, this one, no matter how you train, the error is not going to go down.
Got it. That helps a lot. Thank you.
Yeah. Okay. All right. So let's look at how we apply this to study this polymer chain problem. Okay. So again, to recall, we have this polymer chain stretching, and some of the stretches very quickly, some of the stretches here quickly, and then some of them very slowly. So this is your Z1 or Z star, right? And our key question is we want to build an accurate dynamical model for Z star, and we want to find out what are these closure coordinates that we learn that drives the dynamics. So these are purely of physical interest, right? So we want to, scientists want to know what are the sufficient descriptors of this macroscopic dynamics. And finally, what can we learn from this dynamical landscape, and how can we interact with it? Can we explain why some of it goes quickly and some of it goes slowly? Okay, so first we're going to talk about some simulation data. We performed some simulations on polymer chain stretching, and this is a very well established way of simulating them. And you can see that basically, if you start with some very similar configurations to the naked eye, right, and then you stretch them, some of it really stretches very quickly, and some of it gets stuck, and then it takes a very long time to stretch. And that also this whole thing is random, right? So even from the same initial condition, you could have different outcomes, right, like the last one. And you can see, yes, you can produce very strong heterogeneity in the stretching dynamics. So here again, this is your Z star or Z1, and here is your time. Okay. So what we're going to do is to take this data set and we train this stochastic Onsager net with only two closure variables. That means this Z hat here, this is two-dimensional, and this is one-dimensional. So in the end, what we get is a three-dimensional dynamical system. Okay, so it's a very, very low reduced order description of the entire dynamics, but we found that it works pretty well. So we can use this model and indeed capture this unfolding statistics. For example, if each of this row is an unseen polymer configuration, okay, and then we run it many times, and you can see that the mean and the standard deviation of how fast it's unfolding. So this Z1 is Z star, is the length of the polymer, is captured pretty well. And moreover, if you plot a PDF probability density function of the unfolding time, how fast it's unfolding, you can see that it's also being captured pretty well. Okay, and we can see that this one falls very quickly, so it's a very sharp, distribution near a very small value. Whereas this one falls very slowly, so there's a very large, heterogeneity. So it's a big spread of this unfolding time. Okay,
Faye, you have a question?
Yeah.
Yeah. So this is probably just a rephrase Greg's question. If I understand, the intuition is essentially identify a transformed coordinate system, a change of coordinate system, such that one of them directly corresponding your macroscopic description. But all others is a reduced order representation, yet still valid in that Onsager equation system. I just want to
Yeah,
make sure that.
so this Z star, yeah, that's right. But one caveat is this Z star, we don't have to find them; it's given to us already. So that means
Right.
there is a function that maps X to Z star that's known to us. Like for example, if I give you the coordinate of the polymer chain, then the length is just the maximal X coordinate minus the minimal X coordinate. So this one Z star is already known. So this function is known, right?
Okay.
And this one is learned. And with this one we have to discover it from data. And you're right in that this one here we are trying to find, you can in some sense, a minimal description so that this Z star's coordinate Z star's evolution can be predicted. It does not mean that Z star plus Z hat will entirely summarize this X. Not necessary. It will summarize enough so that Z star can be predicted. Very much like the ideal gas problem, right? If you think about ideal gas, this could be pressure, and these are just temperature and volume. Together, they cannot describe all the air particles that you have, but it is enough to describe pressure.
But then, because you are imposing collectively they satisfy this equation,
yes,
there is a possibility the Z star, since it's already been given to you, therefore is a biased, right? Your model doesn't actually fits perfectly.
Oh yeah. Of course. I mean, in the end, your model only fits approximately. So it's still a reduced description. There's an approximate description. Yeah, that's right. That's right. Yeah, it's going to be errors. Yes.
Okay.
As you can see from the results, I mean, they're not perfect.
Okay.
Yeah. So the ground truth is run by X, right? The ground truth is obtained by just looking at X and reduce them to Z star, whereas the predictions are actually done from the three-dimensional model. Yeah. So
and let me understand. Are you assuming you're assuming a connection between X and Z star? So does it mean the data has to be microscopic to begin with, or you have to have the ability to run a microscale model as part of this process?
Yeah. So our assumption is that we have observations of X, right? So the data, we have the observation of microscopic data, right? So these will be the dynamics of this stretching. So we have a lot of the coordinates here as a function of time.
Oh, I see. I think. I'm sorry. Great. So go ahead.
Oh, no, this makes a lot of sense. But then, so this should not be maybe a better way of describing this is you're not trying to discover a law of nature. You're trying to aggregate a microscale model into a mesoscale model.
Yes. That's right. So we need some data from the microscale, and we don't need any equations. We don't need to know any microscopic equations, but we just need observations on the microscale. And we are trying to learn a thermodynamic description or a macroscopic description of a microscopic process.
And then perhaps the big advantage here is learning a microscale model is infeasible unless you have incredible amounts of data. But learning the closest mesoscale model, presumably, can be done with a fairly modest amount of data. Is that fair?
Yes. And also, I also think that learning the macroscopic dynamics is kind of uninteresting.
Okay, thank you.
Yeah, because in this case, we know the microscopic dynamics. We could write a code to simulate it, but it doesn't really tell you anything about why, for example, some things unfold quickly or not. Yeah, so you can think about actually simulate any system with just like a Schrodinger's equation, but it doesn't really tell us much about the system. Yeah, so this is why even if the microscopic dynamics is known, this is still a well-defined problem.
But then let me understand this thing. It seems like you're going to synthesize a low-dimensional mesoscale description of the system But now these mesoscale things are going to be, well, synthetic. You can't, they don't have a direct physical interpretation. You can't directly measure them. So to what extent can you use them?
Oh, no. These are not mesoscale. These are macro scale. That means it's something that you can directly measure.
So maybe in your dynamics, what were the 3 dimensions?
So the 3-dimensional, so that my dynamics has 3 dimensions, right? So there's 3 variables. One is the stretching, the length of this polymer, which is you can measure in experiment, right? The other 2 are some neural network components, which I will tell you what they mean physically in a few slides time. We can probe what they mean physically.
All right, excellent.
Yeah. So they are all macroscopic, macroscopic. They are not mesoscopic. So these are really thermodynamic description. Okay, it's not like a coarse grained microscopic description. Okay, so it's exactly the next slide. So we know that this 3-dimensional system, right, it can really capture how this polymers unfold. So it's very important, to feel get a feel what they mean. So here's what we can do, right? So because our dynamics, our coordinates from X to Z, they are parameterized by neural networks. So, and one good thing about neural networks is that you can differentiate them. So here's what we can do. We take a polymer configuration X, okay, and we feed it into our neural network to obtain this coordinate Z. Okay, Z2 is going to be the first, learned coordinate, right? The first Z hat coordinate. And we can take a look at what they mean. So what we're going to do is to add and subtract a perturbation of this X, this polymer chain configuration, which is the gradient of your Z2 with respect to X. Okay, so this means that in what way can I perturb the polymer to affect the greatest change in Z2, right? So this is what plus or minus this derivative means. So this means how sensitive is the Z2? What kind of change will bring the biggest change in Z2 in X? Okay, so what we see is this 2 plots. You can see that the shape of the polymer is pretty much the same, but the big difference is that how far these ends are, right? So you can see that here the end-to-end distance is increased, and this end-to-end distance is decreased. So from here, this little experiment, we can hypothesize that this Z2 coordinate has something to do with the distance between the ends of the polymer. And in fact, we can try to confirm this by just plotting a scatter plot of our Z2, which is the neural network output, and the actual end-to-end distance, which we can compute from X. And you can see there's quite a nice correlation between them. Okay, so this shows that Z2 in some sense is some indicator for how far these 2 ends are from each other in the X direction. And we can do the same thing for Z3. And this is slightly more subtle, but if you do the same thing, you can see that, okay, now the end-to-end distance, if you look at the distance between 2 ends, it's pretty much the same, okay? But what's the difference now is that how closed up these 2 ends are, okay? So, for example, here, if you add a perturbation this way, the 2 ends seems to be, so this polymer seems to be more closed up. And here, the bottom one, the polymer seems to be more open up. Okay, so we can actually quantitatively also measure this foldedness by basically the sum of these 2 position vectors. Okay, if their sum is very large, means that they're pointing in the same direction, means that it's really folded. And if the sum is very small, means that they're pointing in opposite directions, which means that it is kind of unfolded. So that's why we call this quantity the degree of foldedness. And we can see that our Z3 is highly correlated again with the degree of foldedness of the polymer. Okay, so in other words, these 2 coordinates that we discover from data, after some careful experimentation, you can actually, impart some physical meaning to it. One of them, it says what is the end-to-end distance, and the one is how folded this polymer is. And our result basically shows that if you know the end-to-end distance, and if you know how folded the polymer is, you can already predict the length, the extension length as a function of time, at least in statistics. Okay, so this is what we find from our data set. So I hope that this sort of answers a bit of your queries earlier.
Yeah, no, it does. In fact, it's kind of interesting. On the one hand, this looks like a very lucky break. Like you were lucky to find this. On the other hand, this looks like exactly how macroscale models of any complex system, social dynamics, ecologies have been developed, except manually. So then my real question is, what about your encoder makes this more or less likely? Is there a way to make this less of a lucky process and more of a reliable thing
Yeah.
that you can make interpretable low-dimensional embeddings?
Yeah, so that's a very good question. So here, I must say that there is a certain amount of luck involved in the sense that there is some simple description that we can find. Okay, so but of course we have tried to make this happen from our model outset, because you remember we use this PCA ResNet. The PCA connection does make this a lot easier, because if you don't add a PCA connection, what we find is that these two things are kind of mixed up together. It's still going to be a two-dimensional system, but each of the coordinate could be some linear combination or even non-linear combination of these two. Okay, but if you use a PCA connection, what we found is that these two components come up much more disentangled. But then that doesn't really take us all the way there, because how do we know these components are something physical? So here we are using something, as you rightly say, is very similar to how we have built macroscopic models all along. Is that we have some quantities that we know could affect the system, and let's try to interpret what the quantity is using some hypothesis generation here, and then to test them using some statistics, right? So this is what we're doing. And our hope is to automate it. But this is not going to be an easy process. I don't have a good idea of how to do this entirely automatically. But yeah, that's going to be an important question. So here, this part is sort of manual. And I should also say that this end-to-end distance part is not that difficult, because end-to-end distance is known to be a descriptor very important in polymers for a lot of other problems. So this one is not. We're kind of we're guessing already that this is going to be important. But this one is something new. Okay, so this one took us a while to figure out. Okay.
Makes sense.
Uh,
A question: have you tried applying this to sociological data, like social networks, that kind of stuff? That's another system where you do have micro data and very crazy macrodynamics.
Yeah, maybe that's something worth studying. So I have looked at, for example, like opinion dynamics models before, but entirely in the microscopic scale. So like basically study on PDEs and interacting particle systems. Maybe there's some macroscopic dynamics that could be learned from there. Yeah. But we have so far we have tested this on like fluid dynamic systems, this one polymer systems, and then currently testing it on some solid lattice kind of systems, but not opinion like social dynamics yet. But yeah, it's an interesting thing for sure.
All right, thank you. That makes sense.
Yeah. Okay. So then there's some other things we can do. So I don't have much time left. So let me just quickly just without going into the details. So for example, we have this energy function that we learned, right? And you can see that we have successfully reproduced the dynamical heterogeneity in the system. So how does this heterogeneity come about? Now we only have a three-dimensional system, so we can actually visualize it. So this energy function tells us that's everything we need to know about the dynamics. So what we found is very interesting. If you plot a fast trajectory and a slow trajectory, okay, so maybe easier to see on this one. So these are just different projections of the energy landscape. It has 3 coordinates, right? So we can only do contour plot for each of the 2 coordinates. So if you look at Z2 and Z3, which is the foldedness Z3 and the end-to-end distance, you can see that there's the fast all the slowly unfolding trajectories, they tend to be stuck near a saddle point. Okay, so you can actually compute using BFGS that these are indeed saddle points, and the fast trajectory just ignores the saddle point; it goes directly into the minimum. Okay, so this is basically different views. So this is the fast one, this is the slow one. It always goes to the saddle point. So in other words, from the landscape, we know exactly what is happening is that if you start your polymer chain configuration is going to be in the Bayesian attraction of the stable manifold, right? So it's near the stable manifold of the saddle point. Then it's going to get attracted towards the saddle point, and it stays there for a long time. And we can also try to understand what a saddle point is. And it turns out that the saddle point is basically, this point corresponds or is a projection of a folded state halfway in the middle. Okay, so that means this it makes a lot of sense, right? The polymer is exactly folded halfway. Then there's a direction where it is stable, which means that if you open out the polymer, it's going to close back. But there's a direction that is not stable, which is when you slowly inches out of it by unfolding in the x direction, right? So this is actually can be rationalized as a settle point in the energy landscape. So in fact, this is true. So if we look at two polymers, so this one is a slow one and this is a fast one, they start from pretty much the same configuration, a little bit different, but one of them gets attracted to the settle point, whereas the other one directly falls into the minimum. And you can see that this the folded one, this state here is very much kind of a halfway folded state, and this is why it's getting trapped. Okay, so we can actually rationalize the landscape directly using what we learned as well. So this is again like, you know, if you have a structure model, you have the energy function, you can look at it. Okay, so this sort of advances the classification of polymer behavior, because currently the only way to do it is visually, right? So the people look at the polymer, you know, as it starts to unfold and try to guess which, you know, position, which kind of shape it is, and from each shape you know exactly, well, you know roughly how they're going to behave. But now we have a quantitative description of the system, which is, you know, you just look at the Z2 and Z3 coordinates and you can see which one falls inside the basic attraction and which one doesn't. And then you can then predict quantitatively what is the unfolding time. This is something we can do. We can do even more than that. Perhaps this is a bit more thermodynamics-like. Is that, remember, our energy function is a differential function because it's a neural network, and we can do Taylor expansion about any point we want. So we could take the Taylor expansion around the stretch state, which is a stable state. Okay, and you can imagine that you know, if we add some energy to the system, let's say, you know, kBt, proportional to the temperature, then we imagine that the free energy will change about the same scale. So delta V will be about kBt, but delta V is a small change in the energy, which can be expanded as Taylor series around small changes in the state. So we could basically ask, if I give the system some thermal excitation of some level T, where T is, you know, sufficiently small, then the change in the state will follow some quadratic function here, and then we can obtain this quadratic function from the neural network. And so this you can think of as a very you know, simple equation of states, right? So kBt is equal to some Z1, Z2, and Z3 changes. And what we found here is that there is some non-trivial correlation between Z2 and Z1 and Z2. That means if you plot this, you can think of this as kind of isotherms, right? You can see that these are not just circles; they are ellipses. So that means that they have some eccentricity here. Okay, so which predicts that if you change Z1, then Z2 also has to change accordingly to some ratio. And later on, we'll see that you can verify this from physical experiments. Okay, this one I won't say too much about it, but you can also do a Taylor expansion around the settle point, and that allows you to design some control protocol to say that, you know, I can give some control protocol to change the way that this unfolding is happening. For example, I can make it unfold quickly or more slowly by looking at how this macroscopic state changes near the settle point. Okay, so the basic idea is that you can switch off the flow near the settle point, and then you will move according to Brownian motion, and then you observe this state Z, and as soon as the Z aligns with the escape direction of the settle point, okay, then you quickly turn on the flow, and you know that will be making it escape much more quickly. And this is what you can do, and you can show it from computation simulation that this does change the speed at which it unfolds. Okay, so something that we can control, at least in principle. Okay, in practice, of course, controlling this will require a good camera setup that we're currently working on. Okay, so this bit is we can try to bring this kind of simulation data into real life, and this is my collaborator Kedar has done in the lab, a very amazing setup where we have a microfluid device here, and we put a DNA molecule in the middle, and we stretch it according to some electric field. So basically 4 electrodes here, two positive and 2 negative. So it stretches them, and you can look at you know, these are the actual data that is collected in the lab. of polymer stretching. You can see this is a DNA polymers, and this DNA do stretch at different rates, right? Some of it very quickly, and some of it gets stuck in kind of a loop here, exactly as what we see in the simulations. And our question is, okay, so we have this data set. Can we say something about this data set from our analysis previously? So it turns out we can. So in this experimental data, if you look at the left-hand side, okay, so here, this row and this row, the first row and the third row are two different samples. And you can see from the very start, it's very hard to make out what's happening, right? But as you stretch them, you can see that the first one stretches out, much more quickly, whereas the second one, it kind of gets stuck in a photo state, in a loop, okay, a photo state. But from here, human eye, we cannot really tell these two apart, at least not meaningfully so. But we can say, okay, so now our thermodynamic model has 3 coordinates we can actually estimate from these pictures, which is the chain extension, the end-to-end distance, and the folderness, which we can do. And if you plot them onto our landscape, you can see that the two of them are slightly different, okay? And if you evolve them under our learned dynamical process, you can see that there's two, the trajectories, the speed at which it unfolds is actually a little bit different. And in fact, this one that gets stuck did really unfold more slowly on average. Okay, so although these are not quantitatively correct, so I have to say that this are not quantitatively correct because the model polymer that we are training on is not the same as the details are not the same as actual DNA polymer, time scale and length scale wise, but it does tell the difference. That means our thermodynamic description does seem to have some indication of reality here in a real polymer. There is some difference between the two. And further, this one is a lot more accurate. Is that if you think about, if you remember our isotherms of this fluctuation, right? We predicted that the Z1 and Z2 coordinates, which we can again extract from experimental data, they are highly correlated in some fashion, okay? And what we showed in experimental data from both the first source, which is what we produced in this paper, and the second source is what people have produced the previous papers, they all fall on this isotherms. Pretty much, the correlations are correct. Okay, so this is something that is, again, purely produced by a tailored expansion of the neural network, but it is in some sense representing a reality. Okay, so I think I'm almost done here. So let me just summarize. So here, we give a method, a general method to build custom macroscopic or thermodynamic description of a dissipative dynamical system. So we can apply this to a variety of systems, not just polymers. Okay, so and this allows us to, not only to predict the outcome of a macroscopic system, but also to understand what are the sufficient descriptors, how to interpret them, and maybe how to analyze them, how to control them. So ongoing work is to try to actually control them, in real time and manipulate the polymers. So that's something that we're doing right now. Okay, so other application of this idea, how do you learn macroscopic coordinate dynamics, similar systems like really Banach convection, and also self-healing materials. We've done some work on that. Okay, so with that, thank you very much for your attention, and I'll be happy to answer any other questions.
No, thank you very much. I guess the one last thing I have is just a really comment is this seems to be very applicable to a lot of economic problems where you have a lot of data. It's just incredibly chaotic. I'm thinking stock market behavior, bank runs, crowds rushing out of a theater, things that you can, in theory, vehicular traffic. You may have a lot of data, but very poor aggregate model of the system, which I guess might actually give you the aggregate model.
Yes. This approach, I mean, this principle kind of generalized, maybe generalization of this approach, yes, will be, that's the goal, right? So we want to be able to bridge between this microscopic scale and something macroscopic that we can easily use for not just understanding, but also to manipulate the system, right? So, yeah, I agree. That's something that, of course, we want to expand the applicability to a variety of systems. Yes.
Right. All right. Well, cool. Yeah. Thank you very much. This is fantastic.